Well, in this week's Chem 100 lab, we're going to explore an interesting class of compounds called hydrates. And this will be an experiment that actually gives us our first opportunity to do some quantitative analysis. Up till now, the experiments that we've done have really focused on making observations and making qualitative assessments of the different types of materials that we've explored. And the lab this week will actually be our first opportunity to make some quantitative measurements, do some, in particular, mass measurements, and use those mass measurements to do some calculations that let us learn a little bit about a particular hydrate that we'll be working to explore. And quantitative analysis is a big part of the development of science and of characterizing chemical materials. So let's think for just a moment or talk for a moment about what hydrates are. When we've talked about compounds in class, typically we talk about ionic compounds where those elements in that compound are held together by electrostatic interactions between a positively charged cation and a negatively charged anion that come together to form that ionic bond. Or we might talk about covalent compounds where electrons are being shared between two atoms because neither one of those atoms is strong enough to rip the electron away. And so those electrons end up being shared in an attempt to fill valence shells and forming a covalent bond. Hydrates are a different class of compounds that utilize properties somewhat from both of those areas. Whenever you hear the term hydrate, you're probably put it in the context of being sure that you stay hydrated, and that means drinking enough water, drinking enough fluids, so that the biochemical processes going on inside your body can behave as we expect them to behave. Well, hydrates, as we're going to deal with them in lab this week, also involve water, but in a little different way. Compounds that we refer to as hydrates are compounds that have molecules of water incorporated in their solid crystal structures. Typically, these are ionic compounds that have a certain number of waters that, when this compound solidifies, that become captured, become encased in that crystal structure. And that gives these compounds some useful properties. These are used often for drying agents. So we can put the version of the compound that does not have the waters incorporated, we call that the anhydrous version, in a humid environment. And water molecules then can begin to penetrate into that solid and be removed from the environment and dry that material. You'll often find drying agents in packages of materials you might order from Amazon or something like that to help keep that material dry. And so these are really very useful compounds, and they also provide an interesting opportunity for us to start to do some quantitative analysis to try and figure out in a particular compound how many molecules of water are associated with each formula unit for that ionic compound. And so in this experiment, you're going to do a couple of different types of activities. We'll do some qualitative analysis where we supply some heat energy to a hydrated compound to drive those waters of hydration away and look at the physical property changes that occur when we're dealing with the hydrated compound or the anhydrous salt. And I show you on the bottom of this slide the two different types of hydrates that we'll do these observations for. The one on the left is copper sulfate in its hydrated form. There are 5 water molecules. I will zoom in on this a little bit. There are 5 water molecules associated with every copper sulfate. We indicate a hydrate with this little dot in between them. And we name the compound just as we would an ionic compound. Here, this is copper 2 sulfate. And then to indicate that it is a hydrate, we add the hydrate term as part of the name, and then tell how many waters there are associated with each formula unit of this salt. So in this case, there are 5 waters of hydration. If we supply enough heat energy, we can drive these waters out and convert this nice blue crystals of copper sulfate pentahydrate. And you've seen this in other experiments, in the diffusion experiment in particular, and also in the solutions experiment. And if we supply that heat energy to drive these waters of hydration away, we can produce anhydrous copper sulfate. And it's a white solid, right? So just the only difference between these two materials in these watch glasses is one has the waters of hydration associated within that crystalline structure. The other has had the waters driven out. Okay? And the second hydrate that we'll make some qualitative observations on is cobalt 2 chloride hexahydrate. In its hydrated form, with 6 waters of hydration, right, 6 water molecules associated with every copper 2 chloride, it has sort of a reddish pink color to it. If we were to drive those waters of hydration off by supplying some heat, that compound turns blue. And this can actually be a good indicator of humidity. We can use this as a moisture indicator. Something that is wet is going to turn this copper or this cobalt chloride pink or red. If it's a dry environment, it will be blue. All right, so some very interesting qualitative observations that we can use when we dehydrate hydrates. But we're also going to do a quantitative analysis where we're going to try and figure out how many water molecules are associated with each formula unit in a particular salt. And the salt that we're going to use is magnesium sulfate or hydrated magnesium sulfate. You might be familiar with this as Epsom salts. Epsom salts are hydrated magnesium sulfate. But we're not going to tell you right off the bat how many molecules or how many waters of hydration are present in that compound. All right. We know that there is some number, but we're not going to tell you what that number is. And your task is going to be to make some quantitative measurements to try and determine what that number of waters of hydration is. This X, this number of waters of hydration, really tells us how many moles of water there are for every mole of magnesium sulfate. So the mass measurements that we're going to make are going to be focused on figuring out how many moles of water are present in a particular sample and how many moles of magnesium sulfate are present, right? And qualitatively, this process is going to be very similar to what you do with the cobalt chloride and the copper sulfate. We're going to heat the hydrate up and drive those waters away. But instead of just making qualitative observations, we're going to measure how much water we've driven away. Hey, and this is not an incredibly difficult mechanical process to do, but it does require you to take some care as you're making your measurement. So all of the heating will be done inside a crucible. And you can see a figure on the right here that shows what our experimental setup is going to be. We'll have a crucible, which is a little porcelain container that we will weigh some Epsom salt, some magnesium sulfate hydrate into. So it's going to be important for us to make good mass measurements of the crucible and its contents. We'll clean the crucible first, and then we will place this crucible onto a clay triangle. So our crucible should rest in that clay triangle like so, on a ring stand. And then we'll use a Bunsen burner as a heat source to dehydrate our magnesium sulfate hydrate. And we'll start that process with the lid just cracked to the side so the water that we're driving away can escape and doesn't get trapped inside the crucible. Okay? So this whole process is going to involve a series of mass measurements of the crucible and its contents and a sequence of heating of that crucible to drive that water off. Okay, so a few things that you want to keep in mind as you're working through this experiment. You want to make sure that your mass measurements are reliable. So be sure that you take care to record the mass measurements that are necessary, and that you've got some confidence in those. And you want to make those mass measurements when the crucible is cool. How do you know when a crucible is cool? It can be difficult because a hot crucible and a cold crucible look the same. Okay, so you do not want to handle the crucibles with your fingers. You want to handle them with some crucible tongs like this. I recommend, and I'm handling with my fingers just to get it up into the camera, I recommend using the crucible tongs just to grab the lid with the tongs and set it aside. You can set the lid down onto a clean bench top. That will be fine. And then when you're moving your crucibles, I recommend grabbing the inside like so. These tongs are actually designed because of their little hole to be able to carry a crucible like this. What I have found is that students that don't have a lot of experience, and even people that do, have a difficult time manipulating this combination. And if you happen to squeeze the crucible tongs too tightly, you can cause the crucible to fall off, and then you at best lose your material, at worst break the crucible. So I've always found it's better to be err on the side of caution and just sort of carry the crucible with your tongs like so that you've got a reasonable grip. Okay. But again, those hot crucibles and cold crucibles look alike. One way to see if the crucible has cooled down to room temperature is to use the back of your hand and hold it somewhat close to that crucible. You've got much more sensitivity on the back of your hand than on the front of your hand, because you use your fingers for doing all sorts of stuff throughout the course of the day. But the back of your hand is a little bit more sensitive. So that can tell you if there is much heat being given off by your crucible. Usually if you wait in the neighborhood of 5 to 10 minutes or so, that crucible is going to have cooled down to room temperature. But you do want to handle them carefully. They are fragile. You do want to avoid breaking those crucibles, and you do want to make sure that you're taking the mass measurements at the appropriate times. There are some heating and cooling and waiting stages in this part of the experiment, so it's wise to actually start this part of the experiment first. And then while your crucible is heating or cooling, you can go back and do the copper sulfate experiment or do the cobalt chloride component. That will allow you to use your time most efficiently. You'll also be using a Bunsen burner. You want to make sure that you take care using that burner. Be sure that the gas is off when the burner is not in use. Be sure that you're positioning your crucible relative to the burner at an appropriate height. So the image on the right here shows, maybe an inch, a couple of inches between the top of the burner and the bottom of that crucible. That will allow you to adjust that flame up or down and be able to effectively heat the bottom of that crucible. Now this picture shows the lid of the crucible closed. And again, in our experiment, we want you to keep that lid cracked a little bit, slid off to the edge so that that water vapor can escape. Once you're done heating, you can slide the lid back on to prevent anything from getting into that crucible. Okay, so at the end of our experiment here, we are going to have driven all of the waters of hydration. At least our goal is to drive all of the waters of hydration away from the magnesium sulfate hydrate and have just anhydrous magnesium sulfate. And so the mass of the material at the very end will be the mass of that anhydrous magnesium sulfate. Okay, from all this information, we can figure out how many grams of water that we've driven away. And if we know the mass of water that's been driven away, we can figure out how many moles of water were present. If we know the mass of magnesium sulfate that remains, then we can figure out how many moles of magnesium sulfate were present. And our number of waters of hydration is just a ratio of those two values. The moles of water that we drove off divided by the moles of magnesium sulfate that were present in our hydrate. So as long as you're cautious with making measurements, be careful about handling hot things, this part of the experiment goes actually quite well. And hopefully at the end of the day, you've learned a little bit about making quantitative measurements, but also about hydrates as a whole.